Hello everyone and welcome to my talk for the Cosmology from Home Conference 2020. My name is Cullan Howlett from the University of Queensland, and today I'm going to be talking to you about cosmology with peculiar velocity surveys. So the aim of this talk is to try and convince you that direct measurements of galaxy peculiar velocities allow us to test gravity in the nearby universe and improve over standard clustering techniques, such as using Redshift Space Distortions. So I'm going to start with how we measure these peculiar velocities, then go on to how they can be used for cosmology and some results with current data, and then some forecasts for the future. So, as I'm sure I don't have to remind any of you, we currently have this sort of conundrum where 95% of our universe consists of these dark components, and we're not quite sure whether these are an exotic particle or field, or if they can be resolved with a modification to gravity. One of the primary ways to test this is to measure what we call the growth rate of structure. So this is this parameter normalized, which we call F sigma 8. Here I'm showing the results from the Planck 2018 papers, and you can see we've made a bunch of these measurements at a variety of different redshifts. So redshifts on the x-axis here, and at the moment and in the gray band there, we're comparing them to the prediction from General Relativity. And so the reason we can do this is General Relativity gives very strong predictions for the growth rates, as given by this equation on the right here. And in particular, it says that it evolves only with the matter density, so omega m to the power of 0.55. So that's its time evolution. And that it's scale independent. And here I put mostly because there are some caveats to this, such as neutrinos, which do add some scale dependence. But for most purposes and on large scales, GR predicts a scale-independent growth rate. And so peculiar velocities, so these are the peculiar motions of galaxies in departure from the Hubble flow caused by local overdensities. These are sourced by gravity, and so they offer a novel way to test the time and scale evolution of the growth rate of structure and confirm or falsify general relativity. And really, everything in this talk boils down to this equation. Here, well, on the left, you've got the divergence of the velocity fields, which we can measure with peculiar velocity surveys, as I'll get onto in a minute. And on the right, you have the density field, which you can either model or you can measure with redshifts. And the relationship between these two contains the growth rate of structure, which we want to measure and use to test GR. So peculiar velocities can be inferred from empirical distance measurements and an observed redshift. So there are many ways we can get empirical distances, the most famous of which is type 1a supernovae, which I'll get onto in a minute. But regardless of the method that we use, they are a direct measurement of the matter fields. So gravity only cares about the total amount of matter, not what component is split into baryons or dark matter. And that means that these measurements are independent of galaxy bias. And what we can also do is we can combine direct measurements of peculiar velocities with redshifts to perform this sort of multi-tracer technique. So we basically have two things measuring the same underlying matter fields, and so that overcomes cosmic variance. An example of this sort of distance indicator is shown in the right-hand plot here, where I'm showing the Tully-Fisher relation, which is a relationship between the rotation speed on the x-axis here of a spiral galaxy and its intrinsic luminosity. So by measuring the rotation speed of a galaxy, we can infer its true intrinsic luminosity. We can then compare that to its apparent luminosity, and from there we can get its peculiar velocity. This is an empirical relationship, so it has to be calibrated. And so this is an example here of the calibration, which for the Tully-Fisher relation is just a straight line. This sort of makes this point a bit clearer. So basically what you do is on the x-axis, you can plot the true distance, which you infer from your distance indicator. On the y-axis, I'm plotting the distance you would infer from a galaxy's apparent magnitude and a cosmological model. And the deviation from this one-to-one line encodes the peculiar velocity. And so these sort of measurements are currently limited by small numbers, and there's also a lot of intrinsic scatter in these relationships. They're empirical, which means they have to be calibrated, and there's lots of astrophysical processes which can introduce intrinsic scatter, and we don't fully understand a lot of these. And so in total, there's about 20,000 peculiar velocity measurements to date, but they have varying selection functions. They use different distance indicators, and they also have different intrinsic scatter and reliability. Some other examples of these kind of empirical distance measurements are the fundamental plane. So this is a relationship between the effective radius of a galaxy, shown in RE here, the surface brightness, I, and the velocity dispersion. And here, a peculiar velocity basically makes your galaxy appear smaller or larger than it truly is. And so it's an offset in the RE direction here. Another famous one is type 1a supernovae. So here's the famous Hubble diagram where you show the redshift and the distance modulus. And the peculiar velocity here just scatters your supernova about the Hubble relationship. So up or down in this plot. So there are ways we can get peculiar velocities directly. So how do we use them? Okay, so there's a bunch of different methods. The first one is we can just do the simplest thing and look at the large scale moments of the velocity. So we can look at the dipole, which is also called the bulk flow. We can look at the shear, which is also called the quadrupole. And in fact, we can look at any number of moments that we wish, but the most common ones are the bulk flow and shear. We can also try and reconstruct the dark matter density field from the peculiar velocities and infer the matter power spectrum. We can do the reverse. So we can take a redshift survey or some map of the density field, and we can try and reconstruct the peculiar velocities the galaxies would have and compare those to direct peculiar velocity measurements. And so we can iterate on that and tune our reconstruction of the density field to constrain our cosmological parameters. Or we can just compute the clustering of both redshifts and peculiar velocities. And so for redshifts, there's been techniques which have been developed over the last 20 years, using things like the correlation function and power spectrum to constrain cosmology. We can do exactly the same thing with peculiar velocities. And so that's what I'm showing in this equation on the bottom here. And this is kind of a key equation that's in fact used for nearly all of these methods. And that's that on large scales at redshift 0, you have this peculiar velocity power spectrum, which you can measure with the peculiar velocities. And you can write this as a function of your matter power spectrum on the right, which you can calculate from theory, or you can measure from redshifts or some map of the density field. And those two things are related by the quantity that we're interested in, which is the growth rate of structure. So in this talk, I'm going to focus purely on this last point, which is the clustering of peculiar velocities. But if you have any questions about any of the other ones, please do get in touch, because these are all also very interesting techniques. Okay, so there's a couple of ways we can look at the clustering. The first method is we can look at the exact distribution of our measured peculiar velocities as a function of their separation, and we can compare to a theoretical covariance matrix or theoretical expectation. So the simplest likelihood we can write down is a Gaussian likelihood. So this is the likelihood of a set of cosmological parameters theta, and it's written as a function of both the measured velocities s here, so this is a vector of peculiar velocities we've measured, and some theoretical covariance, which is a function of cosmology. If you do the maths, you can write down this covariance matrix, and so the covariance between two galaxies at positions xi and xj as a function of your cosmological parameters that you're interested in, and in particular there's an f in here, which is the growth rate of structure, and also the survey geometry, or rather the relative positions of all the galaxies in your survey. And so what you can do is, if you want to infer your cosmology from your measurements, you can choose a set of cosmological parameters. You can calculate this covariance matrix. You can substitute it into the likelihood and calculate the likelihood for that cosmology given your data. And you can do that iteratively for any number of cosmological parameters. And so while this doesn't give you a measurement of the clustering in the sense that you can plot it, it does allow you to maximize the likelihood of a given cosmology. And so this is exactly what we did in 2017 with this 2-mass Tully-Fisher survey. This contains about 2,000 peculiar velocities across the entire sky, except for this sort of small region around the galactic plane. And they're all very low redshift. Here, the maximum redshift of the data is about 11,000 kilometers per second, which is about roughly 100 megaparsecs of reach, or just a bit more. To jump straight to the punchline, here are the results we get from fitting that data. So in red and black here, I'm showing the constraints on the growth rate of structure. So in this top panel here, from the 2MTF survey. The differences between the red and the black are just in how you deal with nonlinearities in the velocity fields. The takeaway is that regardless of what method we use, we find consistent results. And in both cases, we find results that are consistent with the prediction from general relativity, which is shown in the green vertical line. Okay. What you can also do is you can split your calculation of your fitting into different K bins. So you just calculate your covariance matrix for different K ranges, and you fit them all simultaneously, and you can fit the scale dependence of the growth rate. And so this is what we're showing in the left-hand figure, where in dashed, I've got the predictions from general relativity, which are for a scale-independent growth rate. So this dashed line here follows just the matter power spectrum. And in bins, I've got measurements from the 2MTF data, and in all cases, the measurements are consistent with the predictions from GR. So there's no scale dependence from the 2MTF data. And another sort of interesting point is that our constraints are about 1.5 times worse than the 60F Redshift Space Distortions constraints. However, those 60F constraints use about 70,000 galaxy redshifts. Our measurements use about 2,000 pure velocities. So on a galaxy by galaxy basis, the pure velocities really do contain an enormous amount of information on the growth rate of structure. The second method we can use is a method to actually look at the clustering and measure the clustering and make a plot and then fit it. So this is a way of measuring the power spectrum. What you do is you take your velocities, you grid them, you multiply by the line of sight vectors, and you Fourier transform. And then once you've taken that Fourier transform, you can count the power in each cell of your grid, and you can spherically average. So this is a standard technique for calculating a power spectrum. If you do this on the density field, you would recover something like this. So these are measurements from the BOSS DR12 survey using redshifts. So you've got the 3 even multipoles here. So the monopole, quadrupole, and hexadecapole in black of the power spectrum. The points are measurements, and then you fit them with a model, which is the line in this plot. You can do exactly the same with your velocities. However, if you try and bridge your velocities, what you actually find is that you've recovered the momentum power spectrum. And that's because you only have velocities where you've got density or where you've got galaxies. And just because you have no galaxies in a certain grid cell does not mean the velocity there is 0. Okay, the velocity field does not have to be 0 if there's no galaxies there. So what you've actually measured is this quantity on the top right here, which is the momentum, which is basically a density weighted velocity. But it doesn't matter, because this is still actually great for cosmology, particularly because it's linear, it's proportional to the velocity power spectrum on large scales, which is where all the information is. And so what we can do is we can measure this momentum power spectrum and fit it alongside the density power spectrum. And by fitting both of those things simultaneously, we're effectively doing a multi-tracer technique, and so we can overcome the effects of cosmic variance. So we applied this to SUM data in 2019. So this is a combination of the 2-mass Tully-Fisher data from earlier and this fundamental plane data from the 6-degree field galaxy survey. In the top panel, I'm showing measurements and the best fit model for the momentum power spectrum. And in the bottom, I'm showing the measurements and the best fit model for the density power spectrum. And in both cases, we fit these both simultaneously, accounting for the covariance between these 2 sets of measurements and between data points. We find a good fit, so the chi-squared for this fit is good, and we can recover constraints on the growth rate of structure, as shown here. So the points we measure from the combined 2MTF and 60F data are shown as the red point here. And so these give you constraints at very low redshift compared to redshift space distortions, which are typically up here at higher redshift. An interesting thing to note is that all these measurements in orange are actually also pure velocity measurements, or growth rate measurements obtained from pure velocities. And so at low redshift, the pure velocities are really starting to dominate this landscape. Another takeaway here is that if you were to naively combine all this data and fit what the preferred value of the growth rate is using this gamma parameterization, you would find a slightly higher value of gamma. And so, you know, you should take this with a grain of salt, because we haven't included correlations between any of these data points, even though some of them use the same data. But there is some hint at the moment that the growth rate of structure prefers slightly larger values of gamma. And it'll be interesting in the future to see whether this goes away. So speaking of future surveys, we're going to basically increase the total number of curiosities by an order of magnitude over the coming years, and also increase the number of redshifts we have for comparison with those curiosities and the data robustness. So here I'm listing some example surveys that are planned or have started. And so we have things like the Taipan Galaxy Survey, the Wallaby Survey, DESI, and LSST plus potential follow-up. So just going down the list, the total number of curiosities we have combined is about 20,000. But surveys like Taipan and Wallaby are going to measure both a large number of redshifts in the local universe and also basically as many curiosities as we currently have combined in a single survey or more. DESI as well is also going to basically blow all the other redshift surveys at low redshift out of the water. And so we're going to go about 1 million redshifts below redshift 0.1. And DESI could also get some fundamental plane objects. That's still open for discussion and something that we're working towards. And LSST could possibly get up to 200,000 supernovae at low redshift as well, if the follow-up campaigns can be put in action. So these samples are really going to improve our test of cosmology at low redshift enormously. To demonstrate this, here I'm showing some forecasts for the Taipan survey. So here is a plot of the scale dependence of the growth rate again. And the black points show 60F measurements and predictions. And in colored points, we have the forecast for Taipan. So Taipan's going to improve both the errors we get in each bin and also allow us to go to smaller scales than current measurements. And although rare, Type 1a supernovae are really going to sort of become dominant in this field, I think, over the next few years, especially with LSST, because they're much better distance indicators than Tully-Fisher relational fundamental plane. And they have typical distance errors about 8% compared to 20%. And to really drive this point home, here I'm showing some example forecasts for the 60F Bright Galaxy Survey, which contains 700 objects per square degree. So gray here are existing measurements, red are the forecasts for the DESI BGS. And here's what we could do if we had pure velocities from all LSST detected Type 1a supernovae. Okay, so this is more than 5 times fewer objects per square degree, so about 120. But because we have the pure velocities from these supernovae and they're spread over quite a wide sky area, wider than we could do with DESI BGS, especially at low redshift, we see dramatic improvements in the constraints on the growth rate of structure. However, these are quite optimistic, so a lot of work actually needs to be done to obtain these future samples and control for systematics, but this is something I think we can work towards in the coming years. So to conclude, I hope I've convinced you that direct measurements of galaxy pure velocities allow us to test gravity in the nearby universe and improve over standard clustering techniques. They are obtained from distance indicators such as Type 1a supernovae, Tully-Fisher relation, and fundamental plane. In the local universe, they enable some precise measurements of the growth rate of structure, and they can be combined with or improve upon redshift measurements. They give good constraints from current surveys, and they're going to be even better in the future, and will add enormous value when combined with things like DESI. So if you have any questions about these slides or pure velocities in general, please get in touch. Thanks.